Okay, I kind of got caught off on that last one. We had these three equations that would describe, for simple harmonic motion, where the position of an object will be that's going in simple harmonic motion, what will be the velocity of the object in simple harmonic motion, and what will be the acceleration of the object in simple harmonic motion. And at the end of that last tape, I was just making the point that the maximum A can be, if this is just oscillating between 1 and -1, the cosine function might look something like this. It starts like that and it goes like this. So that just oscillates between 1 and -1, but when we multiply it by A, it goes between A and -A. Okay, so X max, the maximum that position it will be from the origin is A. Vmax, well, if we go look at the equation, the maximum that this is going to be right here is going to be, this will be 1. That'd be the greatest it can be. And so that's going to be negative, it will be A omega. That will be the most that it will ever be, is A omega. That will be the maximum it can be. And the maximum acceleration it can have, remember again, the biggest this can be is 1, so it will be A max is going to be equal to A omega squared. So there you have it. Okay, I have a couple more things to tell you about this. What we did in that one is we started our watch at t. We started our watch when the thing was right here. So at t equals 0, it was here, and it was just about to start to move this way, going back and forth. But sometimes we want to start our watch at different times, at times that are not like that. For instance, if we wanted to have this start here, if it were moving this way at first, comes through the equilibrium position, and we start our watch right there, then it wouldn't be appropriate to say that the x is equal to A cosine omega t. When object is at equilibrium, and moving in the positive x direction, at t equals 0, then, and what I mean by that is this, see how it's at equilibrium and it's moving in the positive x direction, it's heading that way. Then the position function will look like this. What function, sine or cosine, at t equals 0, it's at 0. That would be A sine omega t. Because the sine function looks like this. It starts at 0 and heads into the positive direction. If this is t and this is x, this is the x-axis. Okay, well, if that's the case, then our velocity will be the derivative of this, which is A omega cosine omega t. And the acceleration will be the derivative of that, which will be negative A omega squared sine of omega t. All right, so that is how we describe motion. One more of these. Let's just look at one other instance. Let's say we want to start our watch at t equals 0, not with the thing moving this way, but with the thing moving that way. So let's say at t equals 0, the thing is moving that way. what do you suppose we would want to use for our original x versus our original position function? If at t, it's got to be at 0, but it's got to be moving in the negative x direction. Well, then we would do x is equal to, say this is the function we would want to use. It starts at 0, but it's moving down first. It's actually moving in the negative territory. It's moving toward negative a, not positive a. Okay, this function is negative sign. It's a negative sign function, so it would be negative a sine omega t, which means if we wanted to get the velocity would be negative a cosine a omega cosine omega t, and the acceleration would be, got to take the derivative of that, so it'd be a omega sine omega t. You checking my math here? All right. Hey, in any case, look what the maximum x is. It's still a. What's the maximum v? It's still a omega. What's the maximum acceleration? It's still a omega, oops, squared. Oh, I almost missed that one. Yeah, it's still a omega squared. Okay, well, we'll call it a short video. Thanks, bye.